acceptance is basically corresponds to existence of a path from a start state to a final state. Okay? If there exists a path that spells out the string that you are processing, well, then that means it's going to be accepted. Okay? And remember, whenever we talk about accepting strings, you accept only if you are at a final state at the end of the string, right? If you are in the middle of the string and you're stuck at a final state or some other state and you can't go forward, then that string is not accepted. Okay? So you need to be at a final state when the string ends. Okay? That's why the path that you trace should spell out exactly the entire string. Okay? Not the prefix of the string or a suffix of a string. It should spell out the entire string. Okay? And we are not talking about cycle-free paths or anything like that. Obviously, we accept any path. Okay, so any path that might loop through cycles any number of times, all of that is okay. Okay, so again, it's just a existence of a path in the graph. Okay, so now, of course, we all understand how to do acceptance with the DFA, right? So we don't have to go through how to do that. But acceptance with an NFA, it's not quite clear. So how exactly can we do it? The trick is very simple, right? So all you do is, okay, so the NFA, right? With the NFA, right, what we're talking about is, does there exist a path in this graph from the source, from the start state to the end state that spells out the string, okay? So, because we formulate it that way, if you think about it operationally, then we say, okay, the Flying automata has this ability to do things non-deterministically, okay? Which, in the case of automata, what it means is that somehow it's able to predict the right way to go, okay? At some point, when it sees an A in the string, well, we don't know whether to stay in state 1 or state 2, but the NFA has this ability to predict. At least that's how we kind of understand it. And somehow it predicts, and it will always predict it correct as long as the string itself is acceptable. Okay? If the string is not going to be accepted, then it doesn't matter whether you predict right or wrong. Right? It's never going to be accepted. It's not, the path doesn't exist. Well, how does it matter whether you predict, whether I take, whether I go right or left? If I know for sure, I'm not going to get any better, right? So, but the NFA has this uncanny ability to predict, which path to take. Okay. So how do we? Well, obviously there is no oracle, there is no way to guess. So we need to figure out, if you want to implement it somehow, then we need to have a deterministic way to realize this ability to predict. And the way we do that is by saying, okay, I'm going to say that the NFA could be in any of its states. Okay? So I'm going to say, okay, because at any point I could go left or right, or take branch 1 or branch 2. Then what I'm going to do is I'm going to say, okay, let me keep track of where I get by following branch 1, and let me also keep track of where I get by following branch 2. Okay? So this way, I'm going to keep track of a set of states that the NFA could be in, and then I'm going to extend the path with the next symbol from each of those states, and I keep doing this. Essentially what I'm doing is I'm turning this into a deterministic procedure by essentially enumerating and exhausting all possibilities. Okay? But the only thing is that I'm not doing it like a path discovery problem where I might, if I'm not careful, I might turn this into an exponential problem, right? So because I can, or even unbounded problem where, because if I keep finding paths from source to the final state, there are an infinite number of paths, and I may never get done. But instead of trying to enumerate the paths, what I'm doing is I'm enumerating the states. And because the number of states is finite, so the emulation is not going to be going to take too much time. So this picture shows exactly how that works. So what we are going to do is there are 3 states, okay, which means that the NFA could be at any time any one of those three states, right? So I only need to keep track of three such ways to go. Okay, so I'm going to keep track of so the paths here. Okay, so I follow path one. Path one says, okay, I'm going to go from A, B, A, B. I'm always going to stay in state one. Okay, and that particular path, of course, is not going to lead to acceptance. Then you can look at another path which stays in state one for the first AB, and then on seeing the second A goes to state 2, and then B it goes to state 3, and it ends up accepting. Okay? And then there's a third path which eagerly goes to state 2 on the first A and then gets stuck. Okay? And we use this symbol which is called bottom to say undefined. Okay? It basically means undefined, and we use it. There are many contexts in which we want to say undefined and we use the symbol. Okay? So the automaton is stuck, it can't do anything, and so we say it's undefined. Okay? So there are different paths that exist, but there is at least one path that accepts, and therefore this string will be accepted by this automaton. Okay? And the same thing can be done here, except that there is going to be only one path, because the DFA is always going to follow only one transition at any time. Okay? And so it's easier to say when it accepts. Okay? So before we talk about how to talk about an algorithm for simulating an NFA, let's point out some differences between NFA and DFA. So NFAs can have transitions that are labeled epsilon. Okay, so these are called spontaneous transitions or non-deterministic transitions, and these transitions can be taken without consuming any character from the input. Right? So that's the meaning of an epsilon transition. In a DFA, you can't have that, okay, because any epsilon transition introduces non-determinism because, well, because it basically says without consuming any input, you can go to some place, right? So that means you cannot uniquely determine the state of the DFA, and therefore you can't support epsilon transitions in a DFA. Okay, so and we also know that for NFA you could have the same character on multiple transitions out of the state. Okay, and of course what that translates in terms of acceptance is that there could be many accepting paths in an NFA, okay? Whereas in a DFA, there is exactly one path that accepts, okay? And as a result, well, obviously, if you try to emulate with DFA, it's easy to simulate a DFA. NFA is harder. So exactly how hard is it? Well, it's, as I said, what you need to do is you need to say that the NFA could be in any of the n states, right? So each time a character comes, you need to say, okay, suppose the NFA is in state 1, okay, where does it go? Suppose the NFA in state 2, where does it go, right? So essentially you have to repeat this n times for each of the possible states that the NFA could be in, okay? So that means matching is going to involve a factor of n, okay? The transitions themselves, taking an individual transition, you can see can be done in constant time with appropriate representation for the transitions, right? So because there is, if you assume that you can figure out which transition to take in constant time, right? There are many ways to achieve that. You can say, I'm going to represent the transitions using an array, and I'm going to say my alphabet is fixed size, and therefore I can determine which transition to take in constant time. Or if you do it in if you represent it as an array, then you don't need to make any assumption about the alphabet size, because you just say you index and you find the right transition, and that transition leads you to the right place. But if you implement it using, say, a linked list, and then you need to search through the set of outgoing transitions from a state, then, well, if you have to assume that the alphabet is of constant size, or else you're not going to make the transition at a constant time. Okay? In practice, of course, you would use something like a hash table or some other more efficient data structure rather than an array or a linked list. But the point is that no matter what it is, you can generally assume that the figuring out which transition to take from a given state of the automaton is a constant time operation, and therefore the recognition time per input string is going to be order of n for a DFA. Okay, so what is m here? M is the string that you're trying to recognize. Okay? So each character you need to figure out which transition to take, so that takes constant time. So if the string has length of m, then you have to do this m times. Okay, so that's why you get the time of order of m in the case of DFA. In the case of NFA, at any time you're not in any unique state. You could be in potentially all of the states. Okay? Generally speaking, you probably are not in all of the states. You're probably in a few possible states. But if you want to compute the worst case bound, then we have to say, okay, the NFA could be in any of its states, and there are n of them, because we assume that the size of the regular expression is n, and we haven't talked about specifically, but there exists an algorithm for constructing an NFA from a regular expression where the size of the NFA is linear in the size of the regular expression. Okay? And using that construction, you will have only n states, and therefore all you need to do is to examine from each of those states what could be the next state. Okay? And as such, you will get a multiplication factor of n, which in some ways doesn't look too bad. Okay? Especially if you look at the first line, which talks about the size of the automaton. Okay? So as I said, the size of the NFA is linear in the size of the regular expression, but the size of the DFA could be exponential. Okay? So there are regular expressions for which the DFAs are of exponential size. Okay? It's not just some upper bound that it's not the case that we couldn't analyze it carefully and therefore we ended up with a loose upper bound. But actually what happens is that there are regular expressions for which the smallest deterministic automaton for matching the regular expression has exponential number of states. Okay? So, and then you can see what the benefits and trade-offs are. So if you spend the time to construct the DFA, then you can match very fast. But if you don't spend the time and you want to keep it as an NFA, then you pay more at runtime. But you can see that the amount you pay in the worst case in terms of space is a lot worse than what you pay in terms of time with the NFA, right? So what that means is that unless you know that exponential blow-up is not going to occur, only then you can use DFAs, right? Because obviously exponential size is not something that we can deal with, right? We just don't have storage. And so, but in practice, there are many cases where the regular expressions, when you convert them into a DFA, they don't blow up like that. And so in practice, you find that there are a lot of contexts in which we do use DFAs because the exponential blow-up is not experienced.